we shall have a look at the non-ideal solutions. Now we have seen what ideal solutions are, what are their characteristic features, etc. And we had also mentioned that it is difficult to achieve, or it is difficult to reach the conditions of an ideal solution. They are not real, in fact. It is difficult to by any solution, it is difficult to fulfill all the requirements for an ideal nature. And most of the solutions, we can say almost all the solutions are non-ideal solutions, or they are also called as real solutions. Okay. Now, whichever solution we have, we come across are all real solutions. And now we'll see what they are. Now, real solutions or non-ideal solutions are those solutions which do not obey Raoult's law. Okay, we do have a Raoult's law related to the pressure and vapor pressure, partial pressure and mole fraction. Now, non-ideal solutions do not obey Raoult's law, and they are accompanied by change in enthalpy and change in volume during formation. Now, for ideal solution, we have said that delta H mixing and delta V mixing will be equal to 0. But here, the delta H mixing and delta V mixing will not be equal to 0. There will be a volume change, or there will be an enthalpy change when we mix two solutions, two liquids together, or two components together to form a solution. Okay, so almost all the solutions will show this feature, and they are formed by the components which differ in their structure and polarity, and also their molecular interaction. Now, we have said that for ideal solution, the structure must be similar, the polarity must be similar, and the molecular interaction between the components and within the component must be the same. But here it will be different. We know that no two components will be structurally the same. There will be a slight difference, and hence they will not be able to fulfill the ideal condition. And so we say that solutions deviate from the ideal condition, and we call it as positive deviation and negative deviation. So the solutions either deviate positively or deviate negatively. In the sense, there will be the values change of delta H mixing, delta V mixing, and also the total pressure, etc. We'll look into detail about all those. Okay, so the Raoult's law says that if the components in the solution are A and B, then the partial pressure of A will be equal to the vapor pressure of pure A. Partial pressure of A in the solution will be equal to the vapor pressure of pure A into chi A, that is the mole fraction. Similarly for B, and the curve, the plot for vapor pressure mole fraction plot will be straight line. You can see here, this we had seen in the last video. Now, when the solutions show positive deviation, okay, they do not show Raoult's law, they do not obey Raoult's law, we know that. Now, in solutions which show positive deviation, the pressure of the vapor pressure of the components, individual components in the solution, and the total pressure of the solution is found to be greater than what has been expected from Raoult's law. Now, in Raoult's law, we have seen the partial vapor pressure moves in the straight line. For component A, it decreases, and component B, it increases as the component B in the solution is added. But here, in solutions have showing positive deviation, the vapor pressure and also the total pressure, vapor pressure of a particular component and the total pressure of the solution is greater than what is being expected. And also, here the delta H mixing and delta V mixing would be greater than 0. That means it will be having a positive value. That means if you mix two solutions together, the volume increases. That is, change in volume will be positive. That means the volume of the solution will be more when you mix the two solutions together. More in the sense, higher than if you mix 10 ml of A and 20 ml of B. If it is ideal, we should get 30 ml of the solution. But if it is a solution showing positive deviation, you will get a total volume more than 30 ml. That's it. Okay, so delta V mixing will be more than 0 or positive. Similarly, delta H mixing. And the reason why they show positive deviation is because A and B, the components, will differ in their internal pressure, polarity, length of the carbon chain, etc. if it is a organic compound, etc. That means there will be structural difference between the components. And the main reason is that the solvent-solvent and solute-solute interaction, that means AA and BB interaction, is greater than solvent-solute interaction, AB interaction. It means the intermolecular force between the two components A and B will be less than the intermolecular force between A and A or B and B. So what happens? When that happens, when you mix A and B together, when A and B interact, the force of attraction is weak. So what will A do? A will increase the escaping tendency, or will help B to escape. Similarly, B will help A to escape because the intermolecular force of attraction between A and B is less. If it was A alone, then what will happen? A and A interaction is so high that A will not allow another A molecule to move out. Similarly for B also. But when you mix A and B together, and if their intermolecular force of attraction is less compared to their intramolecular, between the molecules, not intramolecular, I'm sorry, between AA and BB, then what happens? The A also will be easy to, the escaping tendency of A also increases and the escaping tendency of B also increases. Because of which, the vapor pressure of the partial pressure of A in the solution, of A component will be greater than the expected Raoult's law pressure, that is the P naught A into chi A. And similarly for B. Okay, so that means the vapor pressure increases. Vapor pressure corresponding to A increases. The vapor pressure corresponding to B increases. Alright, so if we plot the graph, a curve for the solution showing positive deviation, what we find is this is for the ideal condition. PA and the partial pressure of vapor pressure of A decreases as the mole fraction of A decreases, and B increases as the mole fraction of B increases. This we have explained, and the total pressure will be between these two. But for an ideal solution showing positive deviation, the vapor pressure curve for A will be something like this. Okay, it will be more than what has been expected. Similarly for B also, it will be more than what has been expected, and therefore the total vapor pressure, the total pressure of the solution will be more than what has been expected by the Raoult's law. Okay, so this will be the vapor pressure liquid composition curve for a solution showing positive deviation. Solutions like ethanol water, ethanol cyclohexane, ethanol benzene, water propanol, all these show positive deviation. That means the interaction between ethanol and water is weak when compared to the interaction between ethanol, or water and water. Interaction between ethanol and cyclohexane will be weak when compared to interaction between ethanol, and cyclohexane. So that's it. And hence the vapor pressure of the solution increases. Vapor pressure of the partial pressure with respect to each component also increases when compared to that of the pure solid component. So that is for solutions showing positive deviation. In a similar way, we can explain for the solution showing negative deviation also. So in solution showing negative deviation, the vapor pressure of the components and the total pressure will be found to be less than what has been expected as per Raoult's law. So delta H mixing and delta V mixing will be less than 0 or negative. That means when you mix 10 ml of A and 20 ml of B, you will get a volume of the solution less than 30 ml. So the delta V mix will be negative. Similarly, delta H mix also will be, the enthalpy of mixing will also be negative. And here also there will be this negative deviation will be shown by components which are structurally different and their polarity is different. All those, the conditions which are there for ideal solution, exactly the opposite of it. And if there is a partial, also if there is a compound formation between the A and B, okay, that means A and B are interacting and they are forming a compound. If that happens, then also we'll get a negative deviation. Now here, the solvent-solvent interaction and solute-solute interaction will be less than the solute-solvent interaction. That's why they form a compound. That means the interaction between AA or the interaction BB interaction will be weaker, will be less than AB interaction. The interaction between A and B will be strong. So what happens when you mix A and B, A will hold B towards itself and B will hold A towards itself. So A will not allow B to escape and B will not allow A to escape. So obviously what will happen? The pressure will decrease. Okay, so the escaping tendency of each component will be decreased by the other component, because AB interaction will be greater than AA and BB interaction. Alright, so the partial pressure will be less than what has been expected by the Rawls law, as per the Rawls law. And so if we plot a graph, what we get, the pattern will be the opposite of what we got for a positive solution for positive deviation. The vapor pressure curve will be in this way, will be less than what has been expected. Okay, and for B also, and the total pressure also will be lower than, less than what is being expected, as per the Rawls law. Solutions having this water HCl. So water and HCl means water and HCl will interact to form hydronium ion and chloride ion, right? Similarly, water and H2SO4, water and HNO3, chloroform and acetone, they are all interact together. Okay, their interaction, their intermolecular force of attraction is more than individual solvent-solvent or solute-solute force of attraction. So the water will hold HCl back, HCl will hold water back. Chloroform will hold acetone back, acetone will hold chloroform back, and they will not be allowed to escape out in the vapor form. Again, hence the solution will show negative deviation. So basically we can say that there will be three types of solutions, ideal and two non-ideal solution, which shows positive deviation and negative deviation. Now consider an ideal solution having component A and B whose vapor pressure is, or vapors also behave ideally. That means in the vapor phase also they obey Rawls law. And if chi A prime and chi B prime are the mole fractions of A and B in the vapor phase, that means chi A, chi B is the mole fraction of A and B in the solution. Chi A prime and chi B prime is the mole fraction of A and B in the vapor phase. Then chi A prime will be equal to PA by PA plus PB. PA means partial pressure of the component A, and which can be equated to PA. We know that if it is obeying Rawls law, since the solution is ideal, PA will be equal to P naught A into chi A. PB will be equal to P naught B into chi B. Similarly, for the vapor pressure of B component B in vapor state, mole fraction of component B in vapor state. Alright, so if we take up this equation of chi prime A and divide the numerator, divide LHS and RHS by chi A, what you get will be this equation, chi prime A by chi A equal to P naught A by P naught A chi A plus P naught B chi B. And now if we divide the RHS by P naught A, what we get will be 1 by RHS numerator and denominator by P naught A. What we get will be 1 by chi A plus P naught B by P naught A into chi B. Now since this is an ideal solution, and if A is more volatile than B, If A is more volatile than B, that means A vapors will be more, right? Then the P naught A, the vapor pressure, the partial pressure of A will be obviously greater than that of B, because A is more volatile than B. If that is the case, if the A is more volatile than B and P naught A will be greater than P naught B, then the denominator part will be less than 1, because P naught B by P naught A, P naught B by P naught A will be less than 1, as P naught A is greater than P naught B. Okay, so altogether the denominator on RHS will be less than 1. And if that, then what happens? Chi prime A by chi A will be greater than 1, because 1 by a smaller number will be greater than 1. Or we can say that chi prime A is greater than chi A. That is, the mole fraction of component A in vapor phase will be greater than the mole fraction of component A in solution, if A is volatile than B. Alright, that's quite obvious when we look at the volatility in nature, because volatile component will escape to vapor state, and the amount of the component in the solution will be less, and the same component will be more in the vapor state. That's it. And this is called Konovalov's rule. Okay, so what does Konovalov's rule say? It's very simple. Okay, it says that in the case of a binary ideal miscible liquid system, okay, it is binary system, ideal system, completely miscible system, the vapor phase will be richer in the more volatile component as compared to the liquid in equilibrium with it. Okay, that means the volatile component will be more in the vapor phase. So the vapor phase will have more of the volatile component, and the liquid phase will be having less of the volatile component when they reach the equilibrium. Okay, that when we think logically, it can be understood, because if two components A and B combined are mixed together and A is highly volatile, A will escape to vapor state, and the component of A in the solution will be less, while component of A in the vapor phase will be more, and that is Konovalov's rule. Alright, so that's for ideal solution. Our non-ideal solution will not obey this one, because it will not obey the Rawls law. Now, so we have seen different types of solutions, and I had mentioned earlier that there are basically three types: ideal solution and the two non-ideal solution. So ideal solution usually are put in type 1, that is almost all the solution which show more of ideal condition. So the total vapor pressure will be intermediate between the pure components. And then type 2 is solution showing positive deviation, and type 3 is solution showing negative deviation. And in type 2, the vapor pressure curve will be, there will be a maxima in the vapor pressure curve, because the vapor pressure of the solution will be greater than the total pressure. I mean, what has been expected by as per Rawls law. And for negative deviation, the total vapor pressure curve will be showing a minima, because it will be lesser than what has been expected. Now this we need to keep in our mind in order to understand the distillation process, etc., the boiling process, etc., of a solution. We'll look into that. Now, I'm sorry for this. When we compare the properties, or the when we compare the ideal solution, non-ideal solution, and solution showing positive deviation and solution showing negative deviation, these are the few properties or few comparisons which we can do. One is interaction. In ideal solution, all the interactions are same. AB interaction, AA interaction, and BB interaction are same. But those solutions showing positive deviation, AB interaction will be less than AA and BB. And for negative, AB interaction will be more than AA and BB. And similarly, the Rawls law, PA will be equal to P naught A chi A, but for positive deviation, PA will be greater than P naught A chi A, and for negative deviation it will be less. And that the delta H solution, enthalpy of solution, will be 0 for ideal solution, positive for positive solution showing positive deviation, negative for solution showing negative deviation. Similarly, delta V mixing, change in volume while mixing. And also one more thing, ideal solution do not form azeotrope, while solution showing positive deviation will show minimum boiling point azeotrope, and solution with negative deviation will show form maximum boiling azeotrope. Now, what is this azeotrope? You would have heard about this. Now, azeotropes are those solutions or that particular solution which do not separate into its components, wherein both the components boil at the same boiling point, okay, with the same temperature. We'll look into that. Now, before we look into the boiling point curve or the azeotrope, the boiling nature, we will just study the vapor composition and liquid composition of an ideal solution. Okay, and of all these three types of solution. So we'll plot a graph of the liquid composition against vapor pressure and the vapor composition against vapor pressure for an ideal solution. Let us see how it will appear. Now we are taking the mole fraction x-axis, vapor pressure in the y-axis, and chi A, that is we'll start from the 100% A to 0% A and 0% B to 100% B, the way we have plotted other curves. And on this y-axis, the vapor pressure will be showing, we have the vapor pressure of the pure component A, and on this side, right side, we'll have that of the pure component B. If this is it, then when we plot a graph of the liquid composition, we will get such a graph, okay, almost straight line, okay. And for when we plot the vapor pressure curve, it will be like this, okay. It will be below the liquid pressure, liquid curve, okay. Now the vapor curve will be below the liquid curve. Now when we try to get the composition of the solution as well as the vapor composition at a particular pressure, say we are going to check what will be the composition of vapor state and liquid state at this pressure. So you draw a line and extrapolate it through the graph, and then you extend the graph to the x-axis, okay. So you get a composition over here, A, that is, this gives us the mole fraction of the composition of the liquid state in the solution at this pressure, right? Mole fraction of the liquid phase at this pressure, and A prime will be the mole fraction of vapor phase at this pressure, right? So when you look at A and A prime, what do you observe? When you look at A, the mole fraction of the component A is less, isn't it? Because chi A is approaching 0 as you go to the right side, while the mole fraction of component A in the vapor phase is more. That is what Konovalov's rule says. So this is the graphical representation of our Konovalov's rule. And you can see here, at no point does the liquid phase and the vapor phase meet, okay, except at the initial point, that is wherein the pure state, that means in the pure state, obviously the composite we'll have only one particular component, okay. So but for non-ideal solution, what we find will be a different scenario. We'll see how the plot will appear for same plot will appear for a non-ideal solution. Let us first take up solution showing positive deviation. Now we are going to plot in the same way. X-axis will take mole fraction, y-axis vapor pressure, and the mole fraction of A increases from left to right, and that of B, decreases from left to right and increases for B. And we have the vapor pressure for pure A and pure B. Okay. And when we plot the graph appears like this. That is at a particular point the vapor curve and the liquid curve meets. Okay, the liquid curve is obviously on top and vapor curve is below. Alright, so at this point the vapor curve and the liquid curve meets, and at this point the composition of the vapor phase and the liquid phase is the same. So there is a pressure at which the composition of the liquid phase and the vapor phase is same, and you can see that pressure is greater than the individual vapor pressure of the individual components, pure components. Okay, so this composition wherein the vapor phase and the liquid phase have the same composition and the pressure is greater than the individual pressure of the individual components, that mixture is called azeotropic mixture. Okay, we'll be looking into more detail about azeotropic mixture later on. So this is how the liquid composition vapor composition curve appears for a solution showing positive deviation. In the similar way, if we look at for the solution showing negative deviation, what we find is the opposite of this. So you can see here, it's just the opposite, because we know that the solution showing negative deviation will have a minima in the vapor pressure. So the liquid curve will be there on top and vapor curve will be below. Okay, and you can find there is a point again here also wherein the liquid curve and the vapor curve meets. Okay, and there is a pressure at which the liquid curve and the vapor curve will have, or the liquid phase and the vapor phase will have the same composition, same vapor pressure, and that mixture is called again azeotropic mixture. But here it is minimum. Okay, lower. The vapor pressure is lower than the individual vapor pressure or partial pressure of the individual or pure component. Okay, for positive deviation it was more, and in ideal solution we did not find such an azeotropic mixture or such a point wherein the composition is the same for vapor phase and liquid phase. Now we need this plot and the concept of azeotropic mixture to discuss about various processes, particularly the fractional distillation process. We'll look into that later on. Hope it is clear to you. Please draw the graph and make yourself thorough. Thank you.